Yeah. After the meeting, we can find it on the recording chat. All yours.
All right. My name is Siddharth. Many of you know me. This is my second presentation here. And X-ray production. X-ray production is an interesting topic. At the same time, it's very important to understand X-ray based imaging modalities like CT, fluoroscopy, mammography, angiography. In this session, we'll talk about the principle of X-ray production, equipment that is necessary for the X-ray production, process of X-ray production, and the spectrum of X-ray. Principle of X-ray production. X-ray is produced when the moving electrons strike metal target. And there are three important conditions necessary for the X-ray production. First, there must be a source of electrons. Second, there should be a mean to accelerate those electrons. And finally, an area to bombard these electrons. And all these conditions are fulfilled in an equipment called X-ray tube, which is an essential part of all X-ray production modalities like fluoroscopy, angiography, CT scan, X-ray. This is a schematic diagram of X-ray tube, which consists of anode part, shown here, and the cathode part. Cathode is made up of tungsten filament. It has focusing cup. Anode is made up of alloy of tungsten. X-ray tube also contains a window through which X-ray beam come out of X-ray tube. It has got a glass envelope containing vacuum and the lead casing. And between lead casing and glass envelope is a oil for heat conduction. And in X-ray tube, cathode provides electron. Generator gives external energy to accelerate electrons. And target metal is anode. So let us talk about the cathode. Cathode is made up of tungsten filament. And when tungsten filament is heated more than 2000 degrees Celsius, the electrons in the outer orbit of the tungsten atom get excited, get energized, and they come out of electrons and form electron cloud around the tungsten filament. And when the potential difference is applied between the anode and cathode, electrons start to move from the cathode side towards anode side. And there are three main reasons why cathode is always tungsten filament. The first one is it's good thermoic emitter. That means when it is heated, it emits electron. This process is called thermoic emission or addition effect. So tungsten is good thermoic emitter. So that means it's good at emitting electrons. And you can see a lot of electrons in the outer orbits of the tungsten atom. Second is it can be manufactured into very thin wire. So it's really easy to heat up. And the third is it has got high melting temperature of 3000 to 422 degrees Celsius. Whereas focusing cup, if you can see here, is made up of molybdenum to focus electrons. It has also got a high melting point, but it's poor thermoic emitter. Anode is made up of alloy of tungsten because it has to withstand a tremendous amount of heat that produces when the electron interacts with the target metal. And it is also positively charged to attract electrons from cathode side towards anode. Window through which X-ray come out of X-ray tube is made up of beryllium with the aluminum and copper to filter out soft X-rays. And these soft X-rays, also called low energy X-ray, do not contribute in the image production, but increase dose, radiation dose to the patient. And finally, the gas envelope, which is a vacuum tube, so that the electron don't have to collide with the air molecule. Insulating oil between lead case and the glass envelope carries the heat produced by anode away via conduction. So that's all about X-ray tube. Do you have any questions? If not, then I move. Yeah.
Soft X-rays, sort of is I guess there's a spectrum, and it just cuts out that lower part of the spectrum so that you aren't getting them going into the patient and not coming out the other side.
Yes, yes. I'll come to that spectrum part later on. So now we'll talk about the process of X-ray production. A current is applied through the cathode filament, which heats up and releases electrons via thermoic emission. And this current is called filament current. And this current determines the availability of electrons in the X-ray tube. So if we increase this current, there will be more electrons available there. And the potential difference is applied between the anode and cathode. So the electrons move from the cathode side towards the anode side. This potential difference is called tube voltage. And the rate of movement of the electrons from cathode side towards anode side is called tube current. And these two parameters are extremely important for the protocol setup, because the tube voltage determines the energy of X-ray photon. If we want energetic, very strong X-ray photon, we want to penetrate a thick body part or our prosthesis or our implant, then we need high energy X-ray photon. So we have to increase tube voltage. In diagnostic radiology, tube voltage usually the tube voltage is from 30 kV to 140 kV. So if it is less than 30 kV, it can't penetrate the body part. If it's more than 140, it will be a high radiation dose for the patient. So first thing, we can increase tube voltage, we can make very energetic X-ray photon. So depending upon how thick the body part is, we have to calibrate what will be our tube voltage. On another hand, the flow of the electron that we call tube current, measured in milliampere, ranges from 600 milliampere to around 1000 milliampere, and it determines the number of X-ray photons. So if we want to increase number of X-ray photon, then we have to increase the milliampere or the tube current. Okay? So there are two important terminology here. And at the anode, electron strike the target material, and 99% of its kinetic energy converted into the heat, and only 1% is converted into X-ray photon. So 99% of electron's kinetic energy is wasted. We don't need that heat. Okay. So what will happen in the anode? When electron interacts with the metallic target, it can interact with the outer shell of the metallic target, inner shell, and the nucleus field. So the electron can interact with the outer shell, that means the outer part of this atom, inner shell, that means K or L orbit, or nucleus field, that means it won't interact with nucleus, it won't interact with electron, but it just interact with the field and deviate its course. So outer cell interaction emits electromagnetic wave, which quickly converts into heat. So majority, 99% of electrons just interact with the outer cell, emit electromagnetic wave, which converts into heat. Inner cell interaction produces so-called characteristics radiation or characteristics X-ray. And this type of X-ray is used in mammography, only in mammography, not in CT, not in X-ray, not in angiogram, not in fluoroscopy. And nucleus field interaction called Bremsstrahlung radiation. It's a German word. The literal meaning is barking radiation. So this is characteristic X-ray, how characteristic X-ray is produced. This blue electron, the bombarding electron, strikes K cell and get diverted. The electron that's heat ejected as a photoelectron, it's called photoelectron, and get absorbed within few millimeters. And this void is filled by the outer cell electron, which moves from upper cell towards lower cell. And the characteristic X-ray is released. And the energy of this characteristic X-ray is will be a difference between K cell and L cell. Okay, so 69.5 minus 12.1. So the energy of this characteristic cell depends upon the binding energy of electrons. So it depends, and binding energy of electrons are different for different metal and material. So it is characteristics for that particular metal. That is why it's called characteristics X-ray. Whereas when there is a nucleus field interaction, also called Bremsstrahlung radiation, the bombarding electron approaches the nuclear field and it loses its kinetic energy, and the Bremsstrahlung radiation produced. Okay. And this Bremsstrahlung radiation is a spectrum of photon energy. There will be zero, there will be maximum. So there will be the spectrum of energies. And in general radiology, except in mammography, 80% of X-ray are emitted via Bremsstrahlung or the barking radiation. So anything here up to here?
So you said mammography uses characteristics.
Yeah.
So what are the main benefits of using characteristics instead of Bremsstrahlung?
Yeah. So there are, in characteristic photon, the energy, it is monochromatic. So all energies are same. Whereas in Bremsstrahlung, it's a range of energy. Okay. So we have in mammography, we have a very homogeneous soft tissue. We don't have bone over there. We don't have any, heterogeneity over there. So it's always good to have a monochromatic X-ray beam to produce a soft tissue image. But the same thing cannot be done with hip or limbs, chest, because we have bone, we have muscle, skin, a lot of things over there. So we prefer Bremsstrahlung in other type of imaging, but in mammography specific, we always produce characteristic X-ray only. So because of the Bremsstrahlung is polychromatic, it's monochromatic.
In terms of the history of X-ray technology, has there been different materials used to reflect the X-rays over time, or has it just been that, I forget what the metal is?
Tungsten.
Tungsten. Has that always been used, or is there better options, or has there been other options?
The best one is tungsten, but different alloys have been used during, historically. So this is also, it's not a pure tungsten in atom, in anode. It's a alloy of rhenium. So different alloys are used, and the only reason is it should be high atomic number, and it must have a very high melting point. So now X-ray spectrum. X-ray spectrum is a graph of number of X-ray photons plotted against its energy. And it has got a maximum energy in the x-axis and the number of photons in the y-axis. It has maximum energy, minimum energy, characteristic X-ray at certain energy for that particular metal. And part of the X-ray is get filtered when it comes out of the X-ray tube. So this is a filtered part of X-ray. Okay. So now we'll see how this X-ray spectrum changes with different parameters. Okay. So if we increase KV or tube potential, there will be increase in the quantity of X-ray photon. There will be increase in average energy, maximum energy, and if KV is great enough, then there will be characteristic X-ray. So increasing tube potential. Whereas when we increase a tube current or MA, there will be increase in the quantity of X-ray photon only. No change in characteristic energy, average energy, minimum energy, or maximum energy. So if we want to increase the number of X-ray photon, we must increase tube current. So what will happen if we increase the filtration? If we put extra filtration, that will create a few number of energy photons, lower energy photons. So lower energy get filtered. So since lower energy get filtered, there will be increase in average energy of photon, and there will be a decrease in the total number of photons. Okay. So lower energy photons get filtered. Because lower energy photon get filtered, the average energy of photon also get increased, and there will be a decrease in total number of photons. So is it clear? So if we increase the atomic number of anode, the quantity of X-ray photon will be increased, and the characteristic energy will be increased because the binding energy of high atomic number material is high than low atomic number material. So in summary, filament current applied through the tungsten filament at cathode to overcome the binding energy of electrons, which is called thermoic emission or addition effect. Tube voltage is applied across the X-ray tube to accelerate the electron towards positively charged anode, which gives them a kinetic energy. The electron strikes the anode, and the energy released via interaction with the anode atom produces the X-ray photon. These X-ray photon leaves X-ray tube through window towards the patient. They pass through the patient to the detector to produce X-ray image, and we'll discuss about the interaction of X-ray with matter in other class. Thank you. So if any question.
So yes, when we get body X-rays and sometimes when there's a lot of half metal hardware in there, we get quite a lot of distortion from the X-ray. Then they'll ask the image to get a clearer X-ray. So is that where there's a lot of metal in there? Do they then have to increase the current to get a better review of the image?
Yeah. So there are different things we have to consider. There might be a photon starvation because the photon cannot penetrate the region of interest. So if the artifact is due to photon starvation, that we should increase the number of tube current to increase the number of photon. But if the artifact is due to thicker body part or thickness of that particular region of interest, then we should consider increasing the tube voltage to increase the penetrating power of X-ray. So it depends. It depends what kind of artifact it is, and it can be a mixed artifact as well. So sometimes you have to increase the tube voltage and the tube current at the same time. So looking at those artifacts, we can define, first we have to identify what artifact is that. And then we can say that what sort of protocol we should change or do in those conditions.
Why are they called barking radiation?
Because it's a measure, 80% of radiation comes as such.
Yeah. No. Yeah.
And I don't know why they still use German word. It's so difficult to pronounce.
X-rays. So with these X-rays, we bombard material with electrons at high speed to release. But is it also a natural phenomenon? They sunlight hitting the material.
Yeah, there are terrestrial radiation. So X-ray is just a radiation. It's an electromagnetic wave of certain wavelength. There is cosmic radiation as well, where we have a lot of X-rays over there. So how it produce exactly, I don't know. But yeah, there are cosmic, terrestrial.
With the
Maybe
sun hitting something, and that the sunlight's photons. So sunlight isn't electrons; it's kind of the reverse effect. So sunlight's sort of the photons hitting something. So as you have photons going through the patient, but I'm not sure if they might energize electrons, which could then go and hit other electrons, which would then go and produce other lower energy photons. So it's sort of an interchange between electron deflections and electron orbital jumps and photons. Yeah, there is a phenomenon there.
Yeah, and we'll come in another class where in the interaction of X-ray with the matter. So even in our body, when we scan with X-ray, there will be the production of X-ray. So it's so negligible and the energy is so low, we generally disregard it, but there is still the production of X-ray. So if I scan my hand and the X-ray scan, there will be the production of X-ray within my hand as well. So we'll talk about this in the interaction of X-ray, how X-ray interacts with the matter. We'll learn that one.
Think of it like sun rays going and hitting the DNA, and then going and kicking out electrons and kicking out your DNA and causing your DNA to mutate. Like that's an interaction with the sunlight photons coming in and changing the matter.
Yeah.
The matter. This is going the other way. This is the electron creating the photon, or hitting the photon.
And a photon also displaces electron and create X-ray.
Yeah.
So that's how, but we just disregard, neglect that one. The energy is so low that, yeah. Thank you. Thanks.
That's all good, Nat? You there, Nat?
Yep. Thanks.
Make all sense?
Yeah, it did. No, it did. Very good. Very good.
Ah, sweet. Now, cool. I might just quickly jump in here and stop the recording.
I'll talk to you later.
Yep, sounds good.
Okay.
Thank you.
Bye.
Thank you. Bye.
Bye.